Hey students, so this week we're going to be covering and kind of combining some of the things that we've been dealing with for the last couple of weeks. So a couple of weeks ago we started with this idea of electricity. And with electricity we talked about positive charges and negative charges and how they move through a circuit. And we talked about how positive charges and negative charges, if they're opposites, they attract, and if they're likes, they repel. And those were some of the very basic things that we did with electrical charge. And then we added to this idea the concept of magnetism. And we talked about how magnets have a north and a south pole, and how, once again, opposites attract and like charges repel. And there was a lot of similarities there. And so this week we're going to be talking about what happens when we take both of these things and we combine them, because it turns out they are actually two different ways of experiencing the same phenomenon. And we call that electromagnetism. So electromagnetism is when we start dealing with electricity and magnets as a single subject instead of keeping them separate like we have been. So in order to explain electromagnetism, we have to start out with two basic rules that, as long as we kind of understand these two basic rules, we can continue to take a look at some of the ways we can use electromagnetism in day-to-day life. So here are our two basic rules. The first rule is that if we have a moving electrical charge, or in the case of a circuit we call this current, if we have moving electrical charges, those electrical charges create a magnetic field. And the second rule is basically the same as the first one, but flipped. If we have a moving magnetic field, that creates an electrical current in any wires that are nearby. So magnetism creates electricity, and electricity can create magnetism. And so what we really are is looking at two different sides of the same coin. We're looking at how electricity and magnetism can work together, and I'm going to go ahead and show you a couple of examples of how we can use these two rules in productive ways. So let's take a basic look at how electromagnets work and why the structure that you're going to see for most electromagnets involves some kind of a coil. So if I have a basic piece of copper wire right here, and I was to run electricity through this copper wire, what I would get is I would get a very, very gradual magnetic field that comes out of this thing. And if I was to put my compass next to it, I could see that it just barely wiggles north and south. So if I have only one wire, this is a very, very weak field that I'm dealing with. So this isn't going to get much done. And since electromagnets frequently relied upon, I should say, to do really, really strong tasks, we need something stronger. So rather than using a single wire and pushing a huge amount of electricity through it, what we're going to do is we're going to use a coil like this. So a coil like this uses hundreds or thousands of loops to accomplish the same thing. And each one of those wires that's in that loop is going to be emitting that little weak electrical or magnetic field. But what happens is, because they're all overlapped so much, is that now my magnetic field lines are going to be super, super close together on both sides of this thing, because I've got thousands and thousands of field lines kind of overlapping. And so now what I have is I have an extremely strong magnet. And the strength of this magnet changes depending on how much electricity I'm deciding to put through it. So what I have is I've got a little box. It's off screen right now, but it lets me control the amount of voltage that I'm going to put through my electromagnet. I can go ahead and hook up one lead here, and I'll put this over here, one lead here, so you can kind of see what's going on here. And I'll move my electromagnet, give you guys a clear background, and if I turn it on, so I'm at 5 volts right now. You don't see a whole lot happening because there's just electricity running through a wire. But if I put a magnet anywhere nearby, it gets sucked in right away. In fact, I can now hold this up, and they kind of slowly flop out. So I have a little bit of a magnet here. It definitely was magnetic, but I want to make it stronger. So if I take that and I crank this thing up to like 10 volts. So I've now doubled the amount of electricity in this thing. Once again, if I've got my magnets here, I just let it go, and they just get sucked right in. And at this point, oh, not quite. We might have to go with more electricity than that. My wires are very unhappy with me at the moment. At this point, my magnet is now able to resist gravity, and those little magnetic spheres that I was using are no longer able to fall out. I have too much electricity flowing through there. Now, the moment that I turn the electricity off, just like I just did, out they come. No difficulty whatsoever. So electromagnets only work when there's electricity flowing through them. So each one of these little wires is creating its own magnetic field, but because I have so many of them in such a small space, they're now creating a very large magnetic field. So that's kind of how electromagnets work in kind of an abstract term. So to show this with kind of a homemade example, what I've done is gone ahead and created an electromagnet out of some stuff that some of you might have at home. I'm going to go ahead and turn on the light so you can see this better. This is just a simple construction nail, nothing too fancy about it, and I went ahead and I wrapped it with some copper wire. Now, this little board has some tiny little pieces of iron in it, and what happens when you pass a magnet anywhere near it is that the iron realigns so that you can see the magnetic fields in the magnet. So you can kind of see as these little pieces of iron are realigning as I move my magnetic ball around. Now, if I take my nail, you can see it is doing nothing. So this nail is definitely not magnetic at the moment. So what I'm going to do is I'm going to go ahead and hook it up to my power source. And if I go ahead and I turn the electricity on, you can see I'm starting to be able to move some of those pieces of metal that are in there. Now, it's not a lot of them. This is not a strong magnet, but it's definitely working. That's at 4 volts. And I could get it more if I decided to put more electricity through it. Now, the moment that I turn the electricity off and I unhook this thing, you'll notice that it has gone back to not having any effect on the board. And that is because this metal, this nail right here, is made out of steel. And steel is a soft magnet, which you might remember from last week. Soft magnets do not keep their magnetic field after the induction, or the thing that's doing the induction is left. So now this is just back to a normal nail that has no effect on the board whatsoever. And so one of the benefits that you see with electromagnets is that you can easily turn them on and off with the flip of a switch. Think about, like, this is a common thing that you see in, some like old school cartoons and stuff. You got like that car that's in the junkyard, and the giant magnet comes down to pick it up, and like as soon as the magnet attaches to the car, it moves it over to the compactor, and at some point it has to be able to drop the car. And so this giant magnet up here, right here, this is an electromagnet. Because when they want to be able to drop the car, all they have to do is flip the switch, and all of a sudden it stops being a magnet. That magnetic field is broken, and the car drops straight down into the compactor. So that's kind of a way of thinking about electromagnets. They're magnets that you can easily turn on and off by just flipping the switch with the electricity. So now let's go ahead and discuss the concept of electric motors. Because electric motors take everything that we've seen so far and they make them something very usable. Because an electric motor is really just a coil of wire plus some sort of a magnet. And if I have a coil of wire and a magnet and I go ahead and use those things together, I can get something that generates a lot of force. And so whether I'm using that to drive a car forward, or I'm trying to rotate something, or move something, or lift something, electric motors just simply use the fact that coils generate magnetism with an existing magnet, and we can start to get something spinning around and something usable. So your classic electric motor inside of all of its container is going to look something like this. I've got a place where I can hook up a positive and a negative side, and then it's going to spin this tiny little axle right here. But you can't see what's underneath this metal casing. And so that's when we need to go ahead and create one of our own so we can see what's going on. So let's go ahead and build an electric motor from scratch so we can kind of see how things work. What I'm going to need is I'm going to need two electrical cables that are hooked up to some source of electricity. So here I've got my positive and my negative side. And I need a coil of wire and something that can hold that coil of wire. So in this case, these are copper plates. And I'm going to be using these copper plates because copper is an excellent conductor of electricity. It was the same stuff that we used for the wire in the earlier example, and oddly enough, this is also copper. This is insulated copper. So I've got an electric hookup. Oops, this one's upside down. The electricity is going to go from one cable through the copper plate. It's going to go around and around in circles inside of this loop right here, and when it does that, it's going to create a magnetic field, and because it's looping over and over again, that means I'm going to have a fairly strong magnetic field that gets created, and then eventually it's going to leave through this copper plate, and it's going to leave and go back to our system. So if I go ahead and turn this on, and once again I'm going to try this at a lower voltage, this is 3 volts, nothing's happening. We know this thing is generating a magnetic field. I can put a compass next to it, and I can see it's generating that magnetic field. But if I go ahead and I put a magnet next to it, and the stronger the better in this case, I can see it starts to create motion. And what I'm going to do, because I keep blowing the fuse on my little electric box here, I'm going to go ahead and turn this down. Let's see, we got 2 volts here. And when I put that magnet there, this thing's rotating magnetic field comes up against this thing's stationary magnetic field, and I get motion. So now I've got something rotating. And so if I was to use this as an engine, I could put wheels on either side of this and it could drive a car. I could hook a crank up to this and I could lift something. I can do work. And so this is how magnetic motors work. All that it takes is that I have electricity moving through some kind of a coil, creating its own magnetic field, and then if I put a stationary magnetic field next to it, there it goes. It just starts to spin. And I can even control the speed of this thing by changing how much voltage I'm using. So if I want it to go fast, I use more electricity. If I'm okay with this slower speed, I can keep it where it's at. Let's go ahead and turn that up. So that's the basics of an electrical motor. Now our final piece of technical wizardry that I have to go over for electromagnetism is something called a transformer. And no, this is not a robot in disguise. This is something that we use to make sure that our houses don't ignite when we put all that electricity from the street into your house. So what a transformer does is it changes the amount of voltage that you are receiving in an electrical circuit. So for a really good example, the voltage lines, the power lines outside of your house are extremely high voltage. And if you were to plug anything directly into those lines, like your phone or your computer or whatever, it would cause it to explode. It's just way too much electricity. So we need that high amount of voltage to go down. And so a transformer allows us to do that using electrical coils and magnets. So what happens is that what I need is I need a metal box This is a metal box, and it's always made out of some soft magnetic metal. So in this case, let's say we're making it out of steel, kind of like the nail that I used earlier. So just like this nail that I used earlier, this thing is not going to maintain a magnetic field unless there's electricity running through it. And then what I do is I bring in a coil of wire over here, and another coil of wire over here. And so here's our basic setup for our magnet. And what happens is, let's say I've got my high voltage source over here. Electricity gets introduced here, it works its way through this coil of wire, that creates a magnetic field. That magnetic field moves through the metal over to here, and as the magnetic field moves through here, it activates that second rule that we talked about, and it starts the electrons inside of here moving, creating an electrical current over on this side. So I start with my high voltage over here, and that's inducing an electrical current over here. And what happens is that, let's say that I want to step down the amount of electricity that I'm using. So I want to have less electricity. If I want that to happen, I just need a weaker induced electrical field. So I'm going to have fewer coils here. So if I have lots of coils on this side, and I have less coils on this side, what happens is that now what comes out of here is low voltage. Because again, I've got a strong magnetic field being induced over here. That magnetic field is traveling through this piece of metal, and when it gets over here, there's fewer coils over here to receive it, so I get a lower amount of voltage that happens. So this allows us to effectively do what is called step up or step down with our electricity, and it changes the amount of electricity. Oops, you guys can't see that. There we go, that's better. So this allows us to effectively change the amount of electricity that we're dealing with. So when you've got really, really sensitive things, like the sensitive electronics inside of your house, you don't have to bathe them in 120 volts of electricity right away. We can go ahead and reduce that amount of electricity that they need so they can continue to be working. But we can still provide all of the electricity to your house using a single power line, which is what you'll see outside of your house. So this is the purpose of a transformer, and the number of coils determines whether we're going to get a large amount of electricity or a small amount of electricity. And there's a mathematical ratio that you can use to figure that out. It's a basic number of turns over here versus number of turns over here. I'm not going to get into that for the sake of our limited class time, but just know that you can use math to predict this if you really wanted to. So, hopefully by the end of this video, you're starting to get an idea of how something like these magnets can power something like this remote control race car. So there's a couple of things I just want to make sure that you leave this lesson with. The first one is the two basic rules of electromagnetism. That if I have a moving magnetic field, it creates electricity in the wires nearby, and if I have an electrical current moving through a wire, that creates a magnetic field on its own. So the two of them really mirror each other very well. You've also seen how electrical motors work, how we can create an electrical magnet, and why it's important that we have a soft magnetic core so that we can turn the electromagnet on and off. And finally, we talked about how transformers work, the ability to step up and step down electricity by controlling the number of coils that we have on either side of that transformer. So, hopefully all of that made sense. If you need any help, go ahead and check out the extra materials that I have attached, and have a good week.